Hello everyone, welcome back to our latest lecture session. So again we are going to briefly summarize what we have been up to in the last couple of lecture sessions. So I believe we are talking about the carbonate system or discussing the carbonate system. Initially we discussed the closed system as in when the relevant aqueous phase is not open to the gaseous phase, right? And we were done with that or analyzed that, and then we moved on to the more complex system where your carbonate system in the aqueous phase can be in equilibrium with your gaseous phase, right? So you can have exchange of carbon dioxide between the gaseous and aqueous phase, and thus that increases the level of complexity in your system. And we looked at the basics with respect to our component balance, right? And we looked at how to analyze the system. Let's briefly again look at that. So we have our system here, and this is our aqueous phase, right? Aqueous phase, and here we have the gaseous phase. So when you have carbon dioxide in the gaseous phase and you have the carbonate system, which I will represent using CO3 total here, and you can have, or you will have change in phase of carbon dioxide from gaseous to aqueous, and we know that carbon dioxide gaseous can dissolve to CO2 aqueous, and obviously that CO2 aqueous would be in the form of H2CO3 aqueous, the acid. And again we know that from our background H2CO3 can dissociate into H plus and HCO3 minus, which can further dissociate and be in equilibrium with H plus and CO3 2 minus, right? So the relevant derivation might seem relevant, relatively complex, but it is relatively simple. We just defined everything in terms of the total component. Why is that? Because only the component is conservative. So in the closed system we only looked at H total for the liquid or CO3 total for the liquid, but for the open system we have another phase which is the gaseous phase, right? So we had H total, or we defined H total as the sum of H total in the liquid phase and also the gaseous phase, and then we tried to correlate that with the change in CO2 or CO3 total or CO2 total between the gaseous and the aqueous phase, and it is as simple as that. And then we conducted the balance again on H total in the aqueous phase, and we analyzed for the system and went through that, right? So I am not going to go through the derivation again, but in the last class or last session we haven't looked at the applications with respect to Vimintek when the system is open. So we will get that done now. So we will move on to Vimintek here, right? So first we will look at the simple case here. So let us say I have H2CO3 in my system. I am going to take an H plus, and let us say the concentration that is going to be equal to 0.001 molal, right? And I am going to add that to the list, and let us say it is going to be H2CO3, right? So it is going to be 2 times. So let me change that, 0.002, add that to the list, and then CO3 2 minus, and we are going to look for the component there, CO3 2 minus, and that is going to be at 0.001 molal, right? And I am going to add that to the list. Let us just check our particular component. So 0.002 and CO3 2 minus is 0.001, and where did we get that from? So we have H2CO3 in the system. So our components now are H plus and CO3 2 minus. So I am conducting the balance with respect to H total and CO3 total, and H2CO3 I am assuming that the initial concentration is equal to 0.001 molal, right? And that is what we have. So H total will be equal to 2 times the initial concentration of H2CO3 initial, and CO3 total is going to be 1 times the initial concentration of H2CO3. And obviously we are not going to go into detail because we have covered this in greater detail in the previous sessions. So this is what we are now putting in, or getting into our system in Vimintek. So we have H total is equal to now 2 times 0.001, that is equal to 0.002, and CO3 total will be equal to 0.001 molal and molal units. So we are now going to switch to Vimintek, and let us edit our list, and I believe we already inputted this earlier, right? So going back to main menu. So this obviously is a closed system, right? So for a closed system the aqueous phase is not open to the atmosphere, or there is no gaseous phase here. So I am going to run Vimintek as it is. So I am going to run it, and let us see what we have. We have a pH of 4.6, right, and that is expected. and we have the relevant concentrations of CO3 2 minus, H2CO3 and HCO3 minus. So as expected, because its pKa 1 is 6.3 and the pH is 4.6, right, you would expect the protonated form to predominate. And what's the protonated form here, please? It's H2CO3. So if you look at the relevant values on VMinTech, the results summary, you will see that H2CO3 predominates, which is what you expect. So let's look at that again. So as you see here at pH 4.6, H2CO3 predominates, 9.7 into 10 power minus 4, and then HCO3 minus 10 times lesser, and obviously CO3 2 minus, the most deprotonated form, is at much lesser concentration now. So anyway, keep in mind that the pH of this particular system is 4.68, right. I am going back to the input menu, and now I am going to change the system, or I am going to change the system such that it's a open phase, or you have an open system, pardon me. So initially I am going to keep the carbon dioxide concentration relatively low, which would be similar to what you would expect in the atmosphere, and let's see if there is any change in the pH. And the second trial, we are going to increase the pH of, increase the carbon dioxide concentration that would be in equilibrium with your aqueous phase. So what would you expect in such a scenario? So if you take a few seconds, you will see that if the carbon dioxide pressure in the gaseous phase increases, you are going to have equilibrium such that carbon dioxide is going to change phase from the gaseous to the aqueous phase, right. And then you are going to have formation of H2CO3, pardon me, and so on, and the relevant acid base dissociations, and thus you are going to have or expect a decrease in pH. So let's try that out now. So here, when it's an open system, you need to go to gases and specify. So here this is the concentration in atmosphere, anyway the partial pressure that you would expect in the atmosphere. So let's first stick with that and go for a trial there. So I'm going to add that, and I'm going to move on. Let me show you again: gases, specify, and add, right. If you want to, you can look at the list of fixed species here, CO2 gaseous here. Now you have the relevant gas that you looked at. So back to main menu, right. I am going to run MinTech, and we see that the pH is 5.6. So what does that mean? Earlier we had a pH of 4.6, I believe, and now we have a pH of 5.6. What does that mean? So it means that the equilibrium is towards the right. So now the carbon dioxide, or the CO3 total, left the aqueous phase and changed phase into the gaseous phase in the form of CO2. So what does that mean? You are having a net loss of your acid from your system. So what does that translate to? It translates to an increase in the pH, right. So that's what we looked at. So let's just look at that once more, please. So what was the case here? So the earlier case, when it was just a closed system at this relevant concentration of 0.002 molar for H total and 0.001 molar for CO3 total, I think we calculate the pH to be around 4.6, right. And but now with the same concentrations, right, but now we have a gaseous phase here, and we mentioned that the partial pressure of that particular carbon dioxide was what now? I think 0.00038 atmospheres or so on, which is similar to what you would expect in nature. And when we calculate that, we saw that at equilibrium the pH was around 5.6. So why is that? Because here the partial pressure seems to be less, right, and you can look at the Henry's constant and so on, or so forth, but we are not going to go into that. So what happened was the CO3 or CO2, let's say, escaped to the gaseous phase. So now you have a net decrease in your acid concentration here, and that's why you see an increase in the pH, right. So now we'll move back to an open system, back to input menu. So now instead of having a relatively low partial pressure of carbon dioxide, I am going to increase the pressure of carbon dioxide, right, or partial pressure of carbon dioxide. So again, think of this or visualize this: you have a lot of moles of carbon dioxide in the gaseous phase and relatively less number of moles of CO3 total in your aqueous phase. So what's going to happen? The equilibrium is going to shift in such a way that the moles of your particular CO2 or CO3 total here obviously are going to change phase from the gaseous to the aqueous phase. So let's look at that. We'll come back to the gases here, and I'm going to specify the gases, but this time the multiple, instead of saying it's 1, I'm going to say maybe it's 100 times, let's say. So anyway, here we are just saying it's enter the partial pressure of CO2 as a multiple of the above. So if I want to go for 0.038 atmospheres, I'm going to say it's going to be 100 times here, and I'm going to add that, right. And now let us see, let us run Mintech, and now again you see that the pH has fallen down to 4.6, right. So, what would be the carbon dioxide concentration in equilibrium with your particular system? So, again we can look at that. So, more or less you could see that when the partial pressure was 0.038 atmospheres, it is going to be in equilibrium with your particular system, which is H2CO3 initial concentration of 0.001 molar, right. Or you can also look at or click on gases here and see that when it is 3.8 into 10 power minus 2 atmospheres, this is the partial pressure of carbon dioxide that will be in equilibrium with your system, given that the relevant species concentration are such, right, not species, yes, species concentrations are such and the pH is such. So, again if I want to decrease the pH further, what do I need to do? I obviously need to increase the carbon dioxide concentration. So, instead of 0.038, let us look at 0.38, I guess. So, I will go back to the input menu and again back to gases and specify, and instead of 100, and let me try out 1000 here, right, add, and back to main menu. I am going to run Mintech, and here you see now a fallen pH, and obviously why is that? Because you are now increasing the concentration of your carbon dioxide in the gaseous phase. So, again the equilibrium has shifted. So, now to reach equilibrium again, what is going to happen? So, the carbon dioxide from the aqueous phase is going to, pardon me, from the gaseous phase is going to shift to the aqueous phase, right. So, now you are going to have H2CO3 produced in the system, and thus you are going to have a decrease in your pH. So, this is what we observed thus far, and that is what we have been discussing with respect to our component balance in our earlier couple of sessions, right. So, now we will move on to titrations. So, what are these titrations about, right? So, I guess if you are a BTech graduate or even a 12th standard graduate, you would have at some point in time conducted titrations, as in let us look at what we are up to here. So, you have a conical flask here, right, and you have some solution here, and then you have the burette, known concentration, and a known compound here of known concentration, right, and here you have a known compound, but unknown concentration, right. I mean more or less the basic setup is this. So, you want to find out the unknown concentration of your particular compound in your conical flask, and how do you do that? You end up titrating it with relevant anyway compound. We are going to choose the compound obviously, but we are going to come back to that later. So, you have a known compound in the burette, known concentration in the burette, and you are going to titrate that and look at the relevant volume and then calculate the equivalent concentration, right. So, this is the basic premise with almost obviously all the titrations, but keep in mind that there are different kinds of reactions that we need to consider. One obviously is acid and base, which we are currently covering, but you can also have other reactions such as the redox reactions, the aqueous complex reactions, or the precipitation reactions. But for now, since we are talking about acid base, we are going to look at those titrations that are relevant to the acid base reactions, and in general obviously acid base reactions are the most widely used kinds of titrations, and we will see why later on. But again we are going to look at a particular set of examples for acid base relevant titrations, right. So, here let us say what are we looking at now. So, as I keep titrating it here, let us say with my burette, and again please pardon my poor drawing skills, right. You are adding, let us say, so let us take a premise here. Let us say I have a known base, example is NaB, right. I have a base in my particular conical flask, and I am titrating it with a known acid HA, let us say, right. I am titrating it with HA, and HA is out here and NaB is out here, right. So, you will keep titrating, people in general use indicators, right, color change, look at color change and so on. So, what happens at that particular point? So, in general at that particular point the pKa of that particular indicator, if you reach that particular point, so you are going to have, let us say, more protonated form, right, as you keep increasing the acid. So, you can observe a color change and so on. But what does that mean though? It means that at that particular equivalence point, or at that particular point when you stop the titration, it means that the amount of acid that you are adding is equivalent to the amount of base in your particular conical flask, right. Hopefully you understand that. So let's just jot that down. So at the equivalence point, so what's going to happen? The amount of acid added will be equal to the amount, or equivalent, I guess. The key is equivalent, is equal to the amount of base that is present in the solution. And because you know the concentration of acid that you are titrating it with, so then you can calculate the concentration of the base present in the conical flask. So again, the key is that it is equivalent concentrations, right? And I think we are familiar with what we are talking about at this stage of the class anyway. So again, amount of acid added would be equal to or equivalent to the amount of base present in the solution. But vice versa, let us say if you had a acid in your particular conical flask, you can titrate it with a base, and so then how can we transform this particular sentence here? The amount of base added would be equal to the amount of acid that is present in the solution, right. So that is straightforward. So again, let us look at one case and try to calculate this equivalence point. So for example, people use different indicators. So why that particular indicator or such depends upon where the equivalence point lies, right. So you need to know or have some prior idea about where the equivalence point is to be able to stop the titration at that point. So you can either use your pH meter and stop the titration at that particular point, right, or you can also use indicator if that particular color change or such phenomena falls within the range of your particular equivalence point. So let us see how to go about that, right. So we are going to look at the example where we have a base of unknown concentration. We do not know the concentration and we want to find that unknown concentration, right, and I am going to titrate it with an acid. HA is my example here of known concentration, right. So what are we trying to get at? We are trying to get at our equivalence point, I guess, right. So we are trying to get at the equivalence point, and how do we do that? So again, the crux of the solution lies in setting up the component balance. So let us go back to that. So in general, we obviously need to identify the species. Species are those compounds which we know at this stage that are at equilibrium in your particular solution, and what will they be? They will obviously be H plus and OH minus, right, and what else? You will have Na plus to the relevant salt, and then you will have the protonated forms of the acid and the base protonated forms, right, and you will also have the deprotonated forms A minus and B minus, right. And from our previous our prior knowledge, we know we need to choose components, and they obviously are going to be H plus and what else please? Na plus and A and B minus, right. You need to choose your component such that you will be able to arrive at your particular species, right, and that is something we covered in great detail earlier. So again, skipping the well, why skip it? So again, what next though? We need to come up with our formation equations, which we are not going to go through now, formation equations, and then we need to get down to writing our tableau, right. And what next? And then the total component balance equations, right. So at this stage we can skip these three aspects and let us write down H total. H total would be equal to the concentration of H plus at equilibrium, that is the key here, minus the concentration of OH minus, right, plus the concentration of HA plus the concentration of HB, again protonated forms of A and B, right. So we have this particular case. Again, what is H total equal to? We want to transform this equation into you know, or remove those variables which are irrelevant to us and substitute them with variables that are relevant to us. So H total, what is that equal to? So that will be depend upon what is it that we are putting into the system, right. So what is the only source of H total? If you look at it, it is the HA that you are putting into the system, or HA naught, let us say. So obviously H total, as you look at from stoichiometry here, or if you look at the component balance too, is going to be equal to A total, right. So here that would more or less mean A total is equal to concentration of H plus minus, and how can OH minus be written as? We know that the water dissociation constant is equal to H plus times OH minus. So thus H plus is going to be Kw by, or OH minus, pardon me, is going to be equal to Kw by H plus, the water dissociation constant by H plus HA, the protonated form of A, and HB, the protonated form of B. So in this case, in what aspects or what other variables do we know that we can express in them in terms of, right? We know that we talked about ionization fractions, right? We looked at alpha naught and alpha 1 for monoprotic acids and bases, so, or the conjugate base, pardon me. So we are going to use that concept here. So what is that again? Let's refresh our memory briefly. So we have alpha naught for a particular acid is going to be equal to HA, or the protonated form of the acid, by the total acid, as in both its protonated forms and deprotonated forms. And what is alpha 1? The second ionization fraction. It is going to be equal to the deprotonated form by the concentration of HA plus A minus, right. So again, alpha naught will give you an idea about the deprotonated fraction of the acid in its protonated form, and alpha 1 will give you an idea about the fraction of the acid present in its deprotonated form, right. So that is what we have here, alpha naught and alpha 1, right. And we know that this is equal to what now? HA by, as you can see from your component balance, that is going to be equal to A total, and this is equal to A minus by A total. I mean, this is from our previous background, so I am obviously not going to go through it in greater detail. So HA, obviously, how can I express this as? If I look at this particular equation, it is going to be equal to alpha naught of A into A total, right, plus HB again, alpha naught of B into B total, right. This is one equation we have here. So I am going to take this particular term out onto the left hand side. So what is that going to be here? We are now going to have 1 minus alpha naught of A into A total would be equal to concentration of H plus minus Kw by H plus alpha naught of B into B total. And the key here is that the sum of the ionization fractions, what do they need to be? So obviously these are fractions, so the sum of the ionization fractions need to be 1. So 1 minus alpha naught of A, right, would be equal to alpha 1 of A. So I am going to substitute that here. So let us go back to that. So alpha 1 of A into A total would be equal to the concentration of H plus minus the OH minus concentration plus alpha naught of B into B total, right. So let us just check that for a second. Alpha 1 of A into A total, H plus minus OH minus concentration plus alpha naught of B into B total, right. That is what we have. So here we are going to make a few assumptions to arrive at our answer. So here since we are adding an acid, right, so I am assuming that the equivalence point is going to be in the acidic region. So we can assume that the OH minus concentration is negligible, right. So that is something that we are going to make, and we are also going to assume that the acid that you are titrating the solution with is a strong acid, and let us see what that means. So here we are now going to assume that the OH minus concentration is negligible, right. And why is that? Because we are adding an acid and the pH will be relatively low, and we are now going to be left with alpha 1 of A into A total is equal to concentration of H plus alpha naught of B into B total, right. So let us try to simplify this further now. We know that we are going to use a strong acid. So what does that mean now? At almost all practical range of your pH, it is going to dissociate, or what does that mean? It is going to stay in its deprotonated form. So what does that tell you about alpha naught and alpha 1? So if it is going to stay in its deprotonated form, what does alpha naught more or less be, I guess? You can guess that it is going to be equal to 0 or more or less nearer to 0, and alpha 1 is going to be 1. Why is that? So we know that alpha 1 of A is equal to the concentration of A minus by concentration of the total acid, right. And if it is a strong acid, it is going to dissociate at almost all the pH range, and so it is only going to stay as A minus, right. And so you see that A minus by A minus more or less, that is going to be equal to 1. So that is what I am going to substitute here. So it is going to now be A total is equal to concentration of H plus alpha naught of B into B total, right. And now we come to the crux of the issue. So at the equivalence point, right, what do you know? We know that the amount of acid added would be equal to the total amount of the base present in the solution, right. So now we are going to use that to simplify our solution or equation here, pardon me. So now at the equivalence point, and you can correct my spellings if I am erroneous, I guess, right. At the equivalence point, you know that A total is going to be equal to B total, right. So now I am going to have B total is equal to the concentration of H plus alpha naught times B into B total, right. And again, taking this term out here onto the left hand side, what will I have here? Again, it is going to be 1 minus alpha naught of B, and that we know is again going to be equal to alpha 1 times of B, right. So what are we going to have here? Alpha 1 of B into B total is equal to the concentration of H plus. So obviously we need to simplify this further, right. And in general we are going to consider that what do we say, B is a weak acid, right. So I am going to say that the pKa is going to be far greater than pH, right. So what does that mean now? So assuming that Hb is a weak acid, and from our background what do we know? That means that the pK of B is going to be far greater than pH, right. So what does that mean? That the Kb is far less than the concentration of H plus. And where do we have or where can we apply this, I guess? So let us write this down here. We know that alpha 1 of B, what is that equal to? The deprotonated form of B, which is B minus, by the concentration of H plus, not by H plus, pardon me, the protonated form of B, which is Hb, and B minus. And from our background we know that that is going to be equal to what now? Kb by concentration of H plus Kb, right. So if Kb is far less than H plus, what does this turn out to be the denominator? I am going to say that it is going to be equal to Kb by concentration of H plus, right. So if I am going to substitute this in this particular equation here, let us see what I am going to end up with. So I guess I am going to have to refer to this back and forth. So Kb by concentration of H plus into B total is equal to concentration of H plus, right. So let us look at that again. We have this alpha 1 B is now equal to Kb by H plus, right, into B total is equal to H plus. So let us simplify this further. Kb into B total is equal to concentration of H plus square, and now taking the logarithm on both the sides, let us say log of Kb plus log of B total would be equal to 2 times log concentration of H plus, right. So what does that more or less transform into? I am going to swap the two sides, right. So let us write that just to simplify my particular calculation here, log Kb plus log B total. And now we know that pH is equal to minus log concentration of H plus. We also know that we are applying pKb is equal to minus log Kb, right. So I am going to substitute those particular terms here. So it is going to be minus 2 pH at the equivalence point, right. This is the equivalence point. So I will say Ep is equal to minus pKb plus log, seems like I am on the right track, log Bt. And so the pH at the equivalence point is going to be equal to 0.5 into log, I guess it is going to be pKb minus log B total, right. So again, what does this mean now? If I know what the base is that I am looking for, or trying to calculate the equivalence point is relatively easy, because if I know the base B, I can calculate I can get the pKb value, which is here, right. And in general, as you see, even though B total has an effect on your equivalence point, the pH of the equivalence point, because the logarithmic scale, its effect is relatively less, right. So in general, if you can have an idea about the base that you are titrating for, let's say, or against, you can come up with your pH of your equivalence point, right, and that is the crux of the issue. And so once you have this pH of the equivalence point, you know when to stop the titration, right, or you can also obviously look for a particular color change or an indicator, so that will have its particular color change at this particular pH, right. So with that we will stop for today, and I will come back to you with the relevant applications or VMinTech in the next session. Thank you.